Alright, starting off here with worksheet A for chapter 15. Number 1, so we got diagram with the right normal distribution. So the area is 7.5%. Find the mean, find the standard deviation. So one thing we got to know right off the bat is these guys are symmetrical, which means left and right are matching. So it means that the mean is always in the middle. So if I add those two numbers together and divide by 2, that's going to give me the mean. So if we add those up, 88.6 and divide that by 2, so 44.3 would give us the mean for that guy. Alright, and then so we still got to figure out our standard deviation. We got two things for this. One is we got some use of calculators that we have to be able to do. The other is when you're trying to find missing pieces like a standard deviation, that's when we go to the formula that's in our formula packet. So let me start with the calculator part. One thing that we know is that the area of each shaded region is 7.5%. So I know that everything from negative infinity all the way up to 36.3 is 7.5%. Anytime you know the percent, that's when we use an inverse normal. So if I hit second, distribution, and choose option 3 for inverse normal. So the area we're given is 7.5%. And since we don't know the mean and the standard deviation on this one, we're just doing the standardized normal for this, so we can use the formula to figure out the rest. Because in order to use the basic features to actually get the exact numbers going into this, you would need to know the mean and the standard deviation. We only know the mean, so that's why we are just using the standard normal numbers in order to figure out some more information here. So if this were a standard normal curve, then that means this number right here would be negative 1.44. So that's in a standard normal curve. And the reason we have to figure that part out is because when you look at the formula packet, we have a formula right here for standardized normal, also known as a z-score. So for this one, we're looking at the z-score. That's what we just found with the negative 1.44. So that was the position for that 7.5% that we were working with. So if this were a standard normal curve, the z-score at 7.5% is negative 1.44. So I'm going to plug in my negative 1.44 for z. And then just continue plugging into the formula. So the x value is the one that we're pulling off the graph. That's the 36.3 that matched up with that z-score that we found, minus our mean, which we already figured out was 44.3. And then that gets divided by the standard deviation, which is what we are solving for. So let me go back to what we were looking at earlier. So this is what we now have. So just by plugging in the information that was given, so that z-score we can use with that inverse normal function. So remember, if this just represents an area of 7.5% in a standard normal curve where the mean is 0 and the standard deviation is 1, you can use that to get a z-score, which is what we did with the calculator. So, but now that we have that information in there, now we can solve for standard deviation. So if I just multiply my standard deviation over to the left, divide my negative 1.44 over to the right, we have our standard deviation. All right, moving on, number 2. So distribution function, trying to figure out what k is. So for this guy, this is one we definitely need to know here. Real popular test questions come from stuff like this, IB questions and everything. So I'm just solving for k. Remember, one thing we know with probability distribution is that everything has to add up to 1 or 100%, because in terms of probability, you always have a total of 100% or 1.0. So we know in setting this guy up, using our probability distribution, I got my probabilities in the bottom row. So I know that k squared plus 0.1 plus 0.2 plus 0.05 plus 0.4 must all add up to 1. And so we're just using that basic, again, that's just the bottom row is your probability, so they always have to add up to 100%. So if we solve that and clean that up, we're going to come out at the end, we're seeing that k squared equals 0.25. So if we do the square root of both sides, then we should be saying plus or minus 0.5 for k values. So should have a plus or minus on it in doing that. And then for part B here, they want the expected value for x. Now that we know what k is, we can sub that back in and get our expected value. So pretty simple on these guys. So you're replacing k with the plus or minus 0.5. In this case, it's not going to matter whether it's positive or negative because you're going to square it anyway, which is going to make it positive. So you could even almost kind of go from this stage right here. K squared was 0.25, so I can now replace k squared with 0.25 to get my setup. So I got the negative 2 at 0.25, plus we got the 1 times 0.1, plus we got 0 times 0.2, so I'm just going to leave that out. Plus we got the 1 times 0.05, plus you got the 2 times 0.4. And so just clean that up, and that would be our expected value. So moving down here to number 3. So weights of lab samples are normally distributed. So we're given a mean weight. We have the standard deviation. So we want to know the proportion of P, or the probability that weighs less than 68.4. So in this case, we can just use basic calculator feature on something like this. This is where that normal distribution function really comes in handy in a calculator. So in this case, if I go under distribution, and I'm going to choose normal CDF, so the C is for cumulative, so because in this case it's everything less than 68.4, so it's a cumulative sum. So I'm going to choose normal CDF. So in this one, if it says less than 68.4, that means I'm going everything below that, which means I can go all the way to negative infinity, which is what that looks like, and then as high as 68.4. So it's everything all the way up to that. They gave us the mean at 78.6 and a standard deviation of 6.42. So if we punch that in, that should give us our probability or proportion, same thing, for this guy. And if we were going to properly write that answer to 3 sig figs, we would say 0.0561 should be the most appropriate answer for that. Part B, so find the weight for which 12.5%, so notice the change in the question is now they're giving us a percent. So that usually means inverse normal when they give you the percent. So it's 12.5% that weigh greater than something, which they're just calling W. So in this case, keep in mind, just throw a little drawing out here to go with this one. So we just know within this normal curve, we know there's 12.5% above W. So we're given an area of 12.5% above W. So one of the things we got to take into account for this in our calculator is that when we do inverse normal, your calculator always wants this area to the left of X. So I have to do 1 minus 12.5% in order to get the area that's going into my calculator to figure out what W is. So that's what it's going to look like when I plug it in. So anyway, if I go back under distribution, so now I'm going to inverse normal since they gave me the area, and I'm just trying to find the x-axis value. So the area we said was 1 minus 12.5%, so I can just type it in like that. Then again, they gave us the mean at 78.6 and a standard deviation of 6.42. And just enter all the way down, and it looks like we're looking at about, looks like 3 sig figs, we would say 86.0. Some of the older methods for this would involve using like the formula for standard normal and z-scores, but really with these newer features in the calculator, we don't have to do all that. So there are definitely some shorter ways. There's going to be some cases where you got to put that formula to use, like we saw in part 1, but if you can just use a calculator, it sure is nice to be able to just do that. So moving on. So number 4, probability on any given day is 3/8. So in a 32-day period, find the probability on exactly 12 days. So for something like this, this is where we get into the binomial function within the calculator. So we're looking at a 32-day period, and so on those 32 days, exactly 12 of those days are days that she rides the bike, which is this probability right here at the 3/8. So big difference you'll see here on part A to part B. One is a exact number of days, the other is a cumulative number of days, because it's anytime you see the greater than or less than, those are the cumulative guys. So for this one here, go back under distribution, and now we're going to go down to the binomial. PDF is for when you have the exact number, like part A. CDF, the next part, is for when you're doing a cumulative number of days, like when it says less than or more than, for something like that. So on this one, we're doing exactly 12 days, so binomial PDF. So number of trials, we have 32 trials. One of the things that will lead you into using the binomial function instead of the normal distribution function is having a number of trials. So that's something that kind of makes this the binomials, that it's not just a one-time occurrence, it's happening multiple times. So that's why we use the binomial feature for these. So there were 32 days. The probability of success was 3/8, and we're looking for that to happen exactly 12 times. And so there's our 0.144% that would occur. And then on part B, if I go back under distribution, now I'm going to go down to the one that says binomial CDF, because it says less than 12. So that just means everything below 12. So one of the things you got to keep in mind for this, well, let me put those in. So same information as before, but now it says less than 12, which means that does not include 12. So that is everything up to 11, which is what we are putting in there. So if it said less than or equal to 12 or something like that where it was inclusive, then we would include the 12, but it just says less than 12, so we can only go as high as 11 on that one. This is talking about days, so we're talking about full days based on the probability that we were given. So we got to stick with whole numbers on this one, so we're only going up through 11 trials for success. And so there's where we get the second part of our answer. So it should be 0.434 if we're going to round that accurately. Let's see, moving on. So we skip number 5, jumping down to number 6. So probability distribution. So they're giving us all that information over there on the right, so they want us to figure out what K is. So remember, with probabilities like this, I know this notation looks confusing, but if you're really plugged in what those X's stand for, we're looking at the probability of the variable with this plugged in. So this occurring with these X's. And so if we start subbing those in, remember, for total probability has to add up to 1. So as we start subbing in the 0, the 2, and the K, so we have the 0 to the third power over 72, which is obviously 0. So let me jump to the next part. So then 2 to the third over 72, and K to the third over 72. So those guys have to add up to 1 or 100%. So now we can just solve that for K. So a little cleanup on that. So 2 to the third is 8. So 8 over 72 could just be the same thing as 1/9. Maybe in this case you would just multiply through everything by 72 to get rid of the fractions. So let's do that. So let's say 8 plus K to the third equals 72. Now I would subtract the 8. So 64, and then the cubed root of 64 is 4. And we were not doing an even root, we were doing an odd root, so we do not put plus or minus on those. So K should just be 4 for that first one. And then the classic follow-up to that is, now that we know what K is, now we can do the expected value for these guys. So now when we start plugging all these in, so now we're looking to see what it would equal with a K value of 4 as we start subbing in the numbers. So we still got the 0 to the third over 72 times 0. So this is where the extra step comes in. So whenever we're doing the expected value part, that's when you got to multiply it by the X term. And so that's where that guy goes in. And now we can throw in the 2 to the third over 72 times 2. And then the last part, now that we know that k is 4, now we can plug that in. So now you got your 4 to the third over 72 times 4. And now a little cleanup on that, little calculator work, and you got your expected value. Moving on, going to number 7. So we got a random variable, normal variable x with a mean of 60 and a variance of 16. Keep in mind that the standard deviation is the square root of the variance. So if I square root my variance, I get the standard deviation of 4. So that's something we got to do to get our standard deviation. So now you know your mean is 60, your standard deviation is 4. The probability of that occurring for less than or equal to k is about 66%. So we're trying to figure out the value for k. So remember, in a normal curve like this one, we got the mean in the middle at 60, standard deviations of 4, and they are talking about an area below k of 66%. So k is somewhere on the x-axis. Below it is 66%. So again, anytime they give you the percent, we can just plug that into an inverse normal feature to get the value for k. So if I go back under, let me clear that out. So if I go back under distribution and choose inverse normal with an area of 66, we had our mean of 60 and our standard deviation of 4. So now if I just hit enter all the way down, we figure out our k value is 61.6. Moving on to number 8. So a set of bookshelves holds 390 books. Probability that it was published in the U.S. is 53%. So find the expected number of fiction books on the shelves. There we go. So expected number, remember we got a formula for that. So quick look at the expected value, or the mean frequency, is number of trials times the probability of success. So for the one that we're looking at right here, we're talking about 390 books, so like 390 trials. And then they're telling us that the probability of success for that happening, or in this case being published, is 53%. So that's it. So just multiply those two together and you have your expected number. Find the probability that there are at most 200 books on the shelf. So again, kind of notice a change in question now. They're talking about at most 200. So for these guys right here, this is where we can use that binomial cumulative frequency for something like this, because it says at most 200. So it's talking about a whole group of answers. But with the wording of at most 200, that means they are now including 200 in that group, because it says you can go all the way up to 200 on the way that that's worded. So if I go into my distribution, my binomial cumulative for this one, so again we have 390 books or trials. The probability of success for publishing was 53%. For this guy, this says at most 200, so we're going all the way up to 200 on this one. So that's all we got to put in, and it should give us our answer. So 0.264 for that one. Moving on to number 9. So a coin is tossed 3 times, and then they're defining the variable x equals 3 if they all show heads, but it's only a 1 if it's anything else. So find the mean of x. So for that one, for the mean of x, again we have the doing like an average of the number of trials times probability of success on this. So in this case, in order to get all 3 heads, remember what that would look like. That means you're looking at heads, heads, heads. So the probability of that happening is only 1 out of 8. So that's the probability for that. So I have the probability of 1/8 times the number of trials for that, which is the 3 that you see right there, plus it could be anything else. So if I did 1 minus 1/8, then that 7/8 represents everything else other than this case right here. So the probability of this happening is 7/8. It's just everything except this. It's the complement to that. So we have 7/8, and the value we were given for that is a 1. And so that's what our setup would look like. A little calculator work would get you the answer for that. Number 10, coin is tossed 90 times. So again, this is where you kind of have to notice right off the bat that we're given a number of trials. So this is where that binomial, either PDF or CDF, tends to come into play on something like this. So find a standard deviation for the number of heads. So remember that standard deviation is the square root of the variance. And so we do have in our packet the variance formula, which is the number of trials times the probability of success times the probability of failure. So 1 minus the probability of success is whatever's left over, which is the complement to that, which is like what I would call the probability of failure. And so there's the formula we're using. We're going to square root it in order to get standard deviation. So that's what we're plugging into for this one. So for this one, you got your number of trials is the n, so there's your 900. And this is just talking about tossing a coin. So in order for just getting heads in general, it's 50-50. So the probability of getting heads is 1/2. The probability of failure or not getting heads is 1 minus 1/2, which is still 1/2. And so that's what our setup would look like. So we can just punch that into a calculator to get standard deviation. And it looks like on that one it comes out to be 15 if we did that one right. So going down to part B, now it says more than 468 heads were obtained. So in this case, more than 468. To do ones like this with the binomial feature that we used, the cumulative feature always goes from 0 up to whatever we're putting in there. So if I go from 0 to 468, that's going to give me basically everything that we don't want. And so then if I just subtract that answer from 1, that would leave me with everything that is more than 468. So when I go to the binomial feature here, so second distribution and then binomial CDF, because it's cumulative, so we had 900 trials and probability of heads. And so as far as the x value, so again, because they really want more than 468, I got to figure out what everything up to 468 is, which is going to be that answer right there. And then I just have to subtract that from 1 in order to figure out what's left over for their answer. So that's where we get the 0.109 if we did that one right. Moving on. All right. Number 11, so we got a group of 245 people, asked randomly, so find the expected number of people born on Tuesday. So obviously there's 7 days in the week, so we're looking at a 1 out of 7 probability for this. So again, find the expected number. That was the formula we just looked at in the last problem, which is your number of trials times the probability of success. So 1/7 that they were born on Tuesday, so just do 245 divided by 7, and that should get you that answer for the first part. And then standard deviation for the number of people born on Tuesday, and again, that's just the square root of the variance. So using that same formula that we used right here, that was variance, and we're going to square root it to get standard deviation. So standard deviation is when we do the square root of the number of trials times the probability of success times the probability of non-success or failure. So that would be my setup, and just punch that into a calculator to get your standard deviation for that one. Going on to 12, so fair dice rolled 510 times. Again, you got a bunch of trials, so that's usually the binomial stuff. So find the expected number of times that a 3 is obtained. So remember, the probability for success on this would be 1/6, because there's only 1 out of the 6 ways to get a 3 on any roll. And so this is really identical to the last problem that we just did. So if you just did your 1/6 times 510, that would give you your expected number. And then for part B, just the same thing that we did on the previous question with that formula. to get the standard deviation of getting the 3. So again, you'd have your 510 is n. Your probability of success is 1/6. And then so the 1/6 would go here, and then your probability of failure would be the other 5/6 left over for that one for number 12. So jumping on to 13. So standard six-sided, six-face die is known to be biased. So probability of now getting a 5 is 1 out of 5 instead of 1 out of 6. So again, you got 100 trials. So X is the number of rolls for which a 5 is obtained. So again, the expected value for that is you got your 100 times the probability of success, which is 1/5. So if you just did 100 times 1/5, that's what that one would be. Part B is asking for variance, which is, again, this formula without the radical. So you just got your 100 trials, and then your probability of success is going to be the 1/5. And then your probability of failure would just be 1 minus a 5th, which is your 4/5. And that would go here. So you just do not square root this one because it does want the variance, not standard deviation. And moving on to 14. So you have your mean of 560. A is like the x-axis value where the probability of anything below that is 64%. So sketch the normal curve for that information, pretty similar to ones that I've done earlier in the video here for similar questions. Remember, you got 50. The 50% mark is in the middle because the mean splits this guy in half. So you got your mean at 560. So there's our mean. And A is a value such that everything below it is 64%. So obviously, if everything below this is 50%, I know that A is somewhere to the right of that, so that everything below that is 64%. So one thing to keep in mind, so you could just put a 64% here and that would be acceptable, but I could also kind of break that up if I really wanted to. Everything below the mean is 50%, so that must mean I got 14% right here between the mean and A, because of that 64%. So another way to look at it. So we now know the variance is 25, which means the standard deviation is 5, because it's the square root of the variance. So standard deviation is 5. So now we can find A to the nearest whole number, and this is just the basic calculator stuff. So remember, they gave us the percent of 64%, which means we're going to use the inverse normal feature of an area of 64%. The mean we know was 560, and the standard deviation we figured out was 5. So I can just put that in to get about 562 is my answer. So going on to number 15. So probability of getting a 4 on a 6-sided die is 10%. Rolled 900 times. So the mean, write down find the mean of 4s obtained. And so again, we know that obtaining a 4 is 10%, so that's our probability of success for this. So the mean, as we've already seen on several other problems, for this guy is just the number of trials, which they said is going to happen 900 times, times the probability of success of getting a 4 is 10%. So that's what all we would have to do to get the mean. So probability that, oops, sorry, we got to do this part. So find the variance of the number of 4s obtained. So again, we have our variance formula. On our formula packet, which just is the number of trials times the probability of success, what we're using is 0.1 on this case, times the 1 minus that, which is the probability of failure. So that's the other 90%. So we can use that to get the variance. So in this case, we're getting 81. So that's our variance. And remember, of course, standard deviation is the square root of the variance. So we know our standard deviation is 9. So find the variance. So that was what we got with the 81. But we're going to use the standard deviation here in the next part. So find the probability of 4s obtained is more than 1 standard deviation above the mean. Well, 1 standard deviation is 9. So more than 1 standard deviation above 90. So 9 above 90 would put you at 99. So that's 99 is 1 standard deviation above the mean. Find the probability that it is more than 99 is what they're asking then. So this is where we can just go to our calculator for this. So remember, we are talking about a group of options here. So we're looking at that binomial feature. So remember what the binomial feature does is it says, let me go to it real quick. So in the binomial CDF, so we have our 900 trials. Probability of success is 10%. So keep in mind what this question is saying. It's saying technically that we're looking at more than 99. So if I want more than 99, that means I want from here on. So in the calculator, the number I put in is from 0 to that number. So the way the calculator would interpret this is going to give me everything from 0 to 99. And then if I subtract that answer from 1, it leaves me with everything beyond that. So in the calculator, I am getting everything up to this number. So as I go from 0 to 99, that means the probability of getting anything from 0 to 99 is about 85.4%. But I want to do 1 minus that answer to see what's on the other side of that. So this would be the probability that it is more than 99. I am not including 99 in my answer because that's not the way it's worded. It says more than 1 standard deviation above the mean, so it's got to be more than 99. So that's why I did everything up to 99 in the cumulative part and then subtracted that from 1 to see what's on the other side. If it said at least 99, well then 99 would have been included in my answer, but that's just not the way it was worded. So this is the way that you're seeing it here is the right way of doing it, and that should be the correct answer. Moving on. Last one here, number 16. So normally distributed. So the probability that we're greater than or equal to 16.65 is this. So that's the probability. We're given another probability right here that of less than 12.5. So find the mean. So one thing we can do for this is just use some z-score knowledge.